Okay, thanks everybody. Thanks to Shitabro and Amit and Somdatta for all the, I don't even remember the names of all the organizers, but thank you all. And this is a beautiful campus. So this is a very diverse crowd. And sometimes I feel that when I'm talking to such a diverse crowd, the best way to adopt is perhaps this Mullah Nasiruddin's way of telling a joke. I should go around and ask you how many of you know this topic and how many of you do not. Maybe you can teach yourself. I think maybe that's what I'll try to do. So I'm Anirban. I am from IIT Gandhinagar. This is our campus. And it kind of, somehow this picture fits in very nicely with what I want to talk about, the generative model of networks, in which we're going to start with some clean and nice way in which we try to define the network, and then what we'll get is really a shadow of it, or rather a stochastic version of it. So, you have received, over the last one day, there's been a bunch of very nice talks on looking at different properties of these networks, right? If I'm not mistaken, a lot of these have been related to, economics and finance, right? So, but when we go through this talk, I think you can keep a bunch of other networks that we see in day-to-day lives in mind, right? Because a lot of the properties that we'll talk about, no doubt, because of the universality of these properties, they do appear in a lot of the financial and economic networks, but we also get to see them in lots of other networks as well. And here are some of them, right? Just some obligatory pictures I'm supposed to show you. So this is the picture of the internet, not the web, the internet. These are autonomous systems in the internet and connection between them. There's roughly, I think, 50,000 of them in the entire world. The yeast protein interaction network, where the nodes represent the proteins and of yeast, and the edges are, if they're involved together you build an edge if these two proteins sort of interact with one another in some reaction, right? And these are the gas pipelines over Europe, right? So, while there's no doubt a plethora of networks in every sphere of human activity and non-human activity, there's a surprising number of common properties across them, and that's where we'll sort of take off, right? And some of these common properties that you already know are as follows, right? A lot of these networks that we see, they typically have a very large connected component, right? If you look at that yeast protein interaction network, there's no particular reason that there should be a large connected component. Well, if you're looking at the gas pipeline network, you could say that there's a large connected component by design. The power grid network, there's a large connected component by design, right? But not all networks are built by design. Internet autonomous systems, maybe yes. The protein network, not necessarily, right? But then, if things are happening stochastically, if things are happening, even more so by independent agents acting on themselves, why do we have large connected components, right? We'll look at some simple models to try to explain that. The next one that we'll take is something that you probably have heard of. This is what we'll investigate, the small world phenomena, or what we typically call 6 degrees of separation. Except that while we look at the beginning, some models that do explain the small world phenomena, we'll go a little bit deeper, right? And we'll go a little bit deeper into what is called the navigable small world phenomena. Right? And I'll explain what this navigability means. Intuitively means that not only are there 6 steps between you and, let's say, Donald Trump, right? It's also that you can easily find these 6 steps. You can easily find this path, right? Why is that? And lastly, hopefully we'll get to this. Probably we'll get to this tomorrow. We'll try to see. We'll try to see some origins of what we call the heavy tail degree distribution, right? Whether you call it a power law, whether you call it a gamma distribution, log normal distribution, that is debatable. But in any case, there's a heavy tail degree distribution that we see in a lot of these networks, and what could be some simple explanations of that. Right? So, and this is where this network generative models come in. See, the goal is not really to try to produce a model that captures all aspects of networks, right? And the goal is not even to sort of have a model that is very accurately predictive, right? I mean, that is definitely a sort of one big area of research, but that's not something that we're looking for, at least in this part of the talk, right? The goal is to see whether there is a simple explanation behind some of the properties that we are trying to, that we're observing, right? And the simplicity is really the crucial term, right? I mean, of course, if you know, I mean, any amount of this learning theory, you know that as we make the model richer and richer, our predictions and our I mean, we could capture more and more of what we observe. We can, I mean, explain more and more the observed data, but somewhere we're losing the simplicity, because at this point, this is more about the, I mean, understanding it scientifically, understanding the intuition scientifically, rather than coming up with a predictive model. This is what you should keep in mind, right? We are going to put this, however, I mean, having said that, I'll immediately go back on my word, and then we'll say that we will put this networks into another use. And I find this also very interesting. I mean, the goal is also that once we come up with some reasonable models, I'll also sort of maybe subvert them into trying to understand why algorithms behave in a particular way on some networks, right? And specifically, for instance, just to sort of plug this thought in your mind, I mean, there's this whole industry of clustering algorithms, right? And some of them work well, some of them work maybe not so well. Is there a way to characterize this difference between between clustering algorithms? That you have clustering algorithm A, clustering algorithm B. I have this kind of network, which one should you be using, right? Should you do this kind of pre-processing before clustering, or should you not? And when should you do it? Right? So can we utilize some of these models to understand the intuition behind some of these clustering algorithms? I'm talking specifically about clustering because that's what we'll show. I mean, this intuition can be taken to other algorithms domains as well. And again, I mean, I'll keep on peppering you with questions. Please feel free to sort of stop me and ask me to speed up or slow down as you may feel. Okay? So there is virtually a zoo of models, right? And of course, I'll not be doing justice to all of this, because my goal is to just whet your appetite with saying that this is an interesting way of thinking about it, right? And we'll introduce you to some of the basic models. We'll introduce you to some methods of arguing about these basic models, right? That if I have this basic model, and if I want to say that how does a graph generated according to this basic model, what should its properties be? So what are the mathematical tools I have at my disposal? Without going into the sort of the very deep theory, there is very deep theory in a lot of these mathematics, in a lot of these techniques. What I'd like to do is I'll show you proofs that are not so much as a formal proof completely, but essentially picks out the kernel of the idea in whatever the mathematical proof behind it is. And I believe that's an important way of understanding proofs at a 10,000 feet level. Okay, so I mean, the first set of models that we look at is essentially something called a GNP model, which you probably have seen. We look at GNP models, the random graph, called the random graph models with the basic random graph models. We look at some variations known as the configuration model. We might get to look at Kronecker model, probably not today. We will also talk about, then there is another bunch of things that we'll get to probably tomorrow, which essentially, which talk about how, that if I think about the graph being created one node or one edge at a time, right? How can I describe methods of creation that capture, that again, sort of are intuitive and capture some of the properties that I see in these graphs, right? And there's at least 3 important ones that we'll cover tomorrow here. Preferential attachment, copying model, and affiliation network-based models. Right? There are big categories of models that we won't touch today. That we won't touch in these 3 or 4 lectures. There's something called optimization-based model, specifically something called a H or HOT model. I've forgotten what the acronym is. Where essentially what it's saying is that look, in what we'll see here, it's the network generation process is going to be purely a stochastic process, right? In the sense that we will not know why a node, or we'll not even try to characterize why a node is doing what it's doing. We'll just say that it's a random process, but it follows this particular this particular distribution, right? And that will explain, that will be enough to explain. However, you can come back and say that no. I should not think about nodes as being dumb agents. I should, as you are mostly economics students, a lot of you are economics students. Can we assign some notion of optimization, rationality, and sort of associate the rationality of the node's decision with this particular optimization criteria that it's trying to minimize, right? There are some methods that do this. For instance, what if I say that nodes are sort of trying to build the network, while trying to minimize some kind of average distance to everybody, trying to establish themselves as the central node in the network, and how will the network look like? So there are some optimization-based models that sort of do characterize networks in this way. These are much harder to analyze, frankly, right? You could do simulations and then try to see how these networks look like. But if you really want to try to sort of give rigorous theoretical statements that under this optimization-based model building, this is how the network will look like, the theorems will be pretty limited. Right? You won't be able to characterize, you might not be able to characterize, you will be able to characterize certain kinds of structures, but pretty simple structures, right? Again, this is not all, right? Because even here, I don't know. Why is the network trying to minimize average distance? Who cares, right? So there is yet another kind of, another step that you could take, and we will not go there even. These are called the game theoretic models of network formation, right? Here again, you sort of say that as, maybe as Anindya has talked about, or maybe some other speakers will talk about, that maybe, the network is really being created because the nodes are trying to do some transaction, and there's particular rules in that transaction that have, in the entire set of transactions that I've sort of put forward, right? And the nodes are sort of trying to optimize that, right? For instance, here is one particular example, right? I'll sort of go back. So the internet autonomous systems, right? So what is an autonomous system? So I'll come back to it. I'll come back to this in the context of this algorithmic game theory networks. So BSNL, this Geo. So all of these have networks of their own. And they are essentially the autonomous systems. However, none of them can really sort of serve all the customers. How about serving the BSNL, the non-BSNL customers? BSNL still has to send network packets from BSNL customers to non-BSNL customers and vice versa, right? What happens? So of course it has to build up sort of some kind of contract between the different autonomous systems. Right? And there are very established game theoretic studies that say that if I try to analyze this autonomous system network formation in terms of the contracts that these networks are getting into each other, right? For instance, in terms of, okay, if I lay this fiber optic cable, I get to use this cable for free. If you want to use it, you have to pay me so much per unit bandwidth, right? If I try to understand the networks this way, can I try to understand how the autonomous system looks like? There are some results than here, right? And this is really the game theoretic decision. The game theoretic direction that we will not sort of go into. And this is where this incentive question comes into play, which is not captured in the first two categories of models that we'll talk about. There is another category of model that we'll talk about here that I have not listed because it falls in this random static model, which is trying to capture the small world network models that we'll sort of say. Okay, so the broad outline is going to be as follows. First, we'll talk about the random graph model and its variations. We'll talk about the small world network models, and this is probably going to take up the 2 lectures today. Tomorrow we'll get to these growth models, the preferential attachment, copying, and the different kind of variation models, the evolutionary models. Any questions? Yeah. So let me just take a poll. So because and I'm doing this because I'm not sure of all of your background. How many of you have done? So I'm sure some of you have done some amount of graph theory. Yes. We won't go deep into it, but some amount of. If I refer to degrees, connected components, all of this are fairly common. How about some amount the basic algorithms course? Yes. Anybody? No. Okay. So good. So we won't use too much of that. And if I use anything, any terminology from, see, this is really a question of terminology. If I use any terminology from there, I'll make sure to clarify that. Else, please stop me, right? When anything gets intractable. Okay. So so let's go forward. So quick refresher of terms. So for now, we will only look at networks as undirected simple graphs, right? Of course, that doesn't capture everything, right? So there'll be a set of vertices, there'll be a set of edges. So give me some input. So tell me what properties, if I just focus on networks, if that's the model of networks I have in mind, what is an interesting property that you see? Networks is a much more general term. That's how I like to think of it, right? What are some interesting properties that I'm immediately losing by going to this view of networks or interactions? You think we're losing? Because in any abstraction, you have to lose something. In any simplification, you have to lose something. What are we losing? I have not gone there yet. I have not said whether nodes are being, whether the edges are independent or not. We have not gone there. All we are saying is that to us, right, a network is only a set of nodes and the edges between them. That's it. Now, while you're raising an important point, that whether the edges are independently connected or not, but I have not sort of said that. That is still possible to capture in our model. Sorry, there was something else. Of course, and we'll see that is important. So we have lost specific characteristics of the node, right? If you think about the Facebook, right? Facebook, one view of Facebook is that it's really just a set of Facebook IDs and who's connected to whom. That is a view that I have. I've lost the view that each Facebook ID is really a user, right? And he or she has a bunch of interests, and a lot of these interests, and what sort of interests they have, what sort of groups that they're interested in will control a lot of these edges, and will control the structure of the network. We have also lost, any relation that is not, sort of any notion of any multi-party relation. Right? So think of writing papers, right? So one view, for instance, if I were saying that, okay, let me try to capture the co-authorship network. I take all of you, all the scientists, and I'll put in an H if they have written a paper with each other. Papers are not written by two people only. Papers are written by a group of people, right? And while I can represent that by saying that, okay, that whenever, if 10 people write a paper together, I'll put in 10 choose 2 edges, right? It's not really an accurate thing, right? Because it's not as if that these 10 choose 2 edges arose independently. It's because that this set worked on this paper together, right? And for that, we have to go from graphs to hypergraphs, right? And there's a lot of work on that also. Not as much, right? But we have lost that. We've also lost that network doesn't exist in isolation, in the sense that what will you do with this network? This is just a skeleton, right? What is really interesting at the end of the day, while studying the skeleton is important, what is really interesting is what happens on the network. As I gave you this Facebook example, Facebook is important only because of the information flow that happens via Facebook, right? So how do I capture the information flow? Facebook or Twitter, and these are the information networks that we'll talk about, and that we'll get to in the. I'll give you one sort of one sort of set of results for that in the evening lecture today, because that is upcoming work, and there we'll try to model we'll see how to try to model information flow in some of these networks, but these are some of the things that we have lost, but let's see what there's still interesting things we can study out here. Okay, so again, this is really all just a refresher of terms, because I'm sure a bunch of you know these. When I talk about the degree of a vertex, it's really the number of vertices it is connected to. When I talk about the degree distribution, it's really the histogram of degrees, right? I'll frequently, in sort of giving you the pseudo-mathematical proofs, pseudo-formal proofs, I'll refer to things called trees, which is really a connected graph without a cycle, and therefore if the tree is of n nodes, it has n minus 1 edges, and so on and so forth. Okay. So what is a connected component? Okay, so because this is really going to be our study of, the first object of our study, because it's really something very, very simple. So connected component is this very simple idea imagine this is a graph, right? The red nodes and the blue nodes taken together, and the black are the edges, right? So this graph, in this graph, these blue nodes are connected to one another, the red nodes are connected to one another, and by connected, I don't mean directly has a direct, every pair of blue nodes does not have an edge between themselves, right? When I mean connected, I say that there is a path that, that goes from one blue node to another. From any blue node, there's a path that goes to another blue node, and similarly for the red nodes, there is no path between these two, right? So in general, for networks that we observe, it's entirely possible that the number of components, these are called components. It's entirely possible that the number of components might be greater than 1, right? It's also entirely possible that if I look at the size of these components, that they'll be like choosing random numbers, right? They'll be like choosing a bunch of random numbers from whatever universe, from the universe which is the size of the entire node set, right? It's like saying that, okay, if I say that, okay, if I have a network of like 1 million nodes, and if I say that, okay, how many components will it have? Oh, it will have like k components, some k, where k will follow some distribution. What will be the distribution of the size of the components? Oh, more or less, each of them will be 1 million by k, sort of some distribution around that average value. That's typically the basic intuition, at least my basic intuition. You're probably more intuitive, right? That's what I'll expect, but that's not really what happens, right? If I happen to look at real networks, right, and this I think, yeah, this is what I was saying. This is, I think, the citation. This is the citation network. So there are edge directions. So forget the directions across. Forget the directions for now, because we're only talking about undirected networks. And this is the physics citation network from high energy physics or something, taken across a number of years, right? See, in here, for instance, nobody actually built this network. Right? It's not like the power grid network where people sort of went ahead and designed the edges so that the power can flow from any point of the network to another. There's no necessity like this. This arose spontaneously. However, we do see that there is there are a bunch of connected components. Each of these things that you see by itself are a bunch of connected components. There is one very large connected component, right? Which is taking, I'll say, maybe constant fraction of the entire set of nodes, right? Basically. Why is that? Right? And this happens not just in this example, not just in this domain, it happens universally. Why does there exist a large connected component which almost always takes up most of the universe, most of the set of nodes that exist? Right? And is there a simple explanation towards that? Right? Oh, by the way, so I have borrowed, abundantly from, this being a pretty established subject and what I'm teaching you being pretty classroom, I've borrowed abundantly from books and pictures, and mostly there are citations, but sometimes I've missed them. I'll sort of put them in when I put up the slides later, if there's any missing citations. So this is what I'll try to explain. We'll try to explain first. Right? And to try to explain, we need to step back a little we need to step into a time machine, and we need to go and meet these two pretty famous mathematicians. I should not have maybe put in their names of at least one of them, Paul Erdős and Alfred Renyi. Right? Erdős was this, what I call the itinerant mathematician who essentially lived his entire life out of a suitcase and went around proving theorems. And it's literally true. So what we'll study is this very amazing mathematical object introduced by them. Very simple, very rich. It's called a random graph model, right? So what is this? This random graph model. So here's this simple definition. It's a 2-line definition, as you can see. It has generated thousands of papers, thousands of theses, right? We say that, okay, let us look at this mathematical object. Right? We'll start with n nodes, and I have drawn them out in a circle. Let me number them 1 to n, because the names are not going to be any important to us. We fix some value p, some probability value p between 0 and 1. So p can be 0. Right? And what we will do is that we will go around and ask each pair of nodes, ij. Right? This is going to be undirected, so each pair will only be sort of approached once. Not ij and ji, only the set ij will be approached once, and they'll be asked to toss a coin, right? They'll be asked to toss a coin to do this. And the coin will give you head with probability P and tail with probability 1 minus P. Right? And if the coin gives you a head, they get to add in an edge between them. Right? This is what we were saying, that the nodes add edges independently. Yes, they do. Right? And that's all. Right? That's it. That's it. So I go around asking everybody to toss this coin, and if it turns out heads, they get to add in an edge. Very simple questions. How many coin tosses overall? N choose 2. So n into n minus 1 by 2. Right? Okay. So number of heads, the total number of heads that we get is a random variable. Right? You understand that, right? Because everybody gets a head or a tail, so the total number of heads is a random variable. Do you know what its distribution will be? A Poisson distribution. Very nice. Yeah, my job becomes easier. And its expectation is going to be, and it's a Poisson distribution because I can write it as a sum of 0, 1 random variables, right? Each of them become P, 1 with probability P and 0 with probability 1 minus P, and therefore a sum of binomial things is a Poisson thing, and its distribution is going to look like this. Its expectation, well, I don't even need to look at this very tough formula because I'm pretty lazy. Its expectation by the linearity of expectations, it's basically n, capital N, which is capital N is n into n minus 1 by 2 times P. So basically n into n minus 1 by 2 times P. That's the expected number of edges. That's it. So now the interesting parts come. Okay? So the graph itself is a random variable, right? Not just these edges. Okay? And in fact, every possible graph of n vertices is assigned a particular probability. Okay? So here is maybe a trick question, right? What setting of P can I have, right, so that every possible graph on n vertices is assigned the same probability? I told you it is a trick question. How can I say, is there a possible setting of the value P? See, my only parameter here is P, right? And the P is same for everybody for now. We'll talk about different P's. So is there a possible setting of the value of P so that so first of all, you do agree with me that every graph on the small n vertices can appear? Of course, right? So basically it appears with some probability, so it assigns that probability. So the question is that, can I set this value P to be something so that every graph gets the same probability, including the null, including the empty graph? That is not always the case. Well, if I set P to be 0, what will happen? If I set P to be 0, what will happen? You tell me. Nothing will be created. So only the empty graph, by empty I mean only the vertices exist, no edges exist. Empty graph gets a probability 1. All other graphs get a probability 0. Right? So P is 0 basically puts all the probabilities on one graph, which is the empty graph. P equal to 1, what happens? On the clique, puts all the probabilities on the clique. So what can I set P to be so that all graphs get the same probability? Huh? How is 0 the answer? I just told you that P equal to 0 puts all probabilities on the empty graph. And no other graph can exist. 0.5, why? 0.5 is the right answer, but why? You can either? Well, I mean, in any case, you can either have heads or tails. That is true, right? I mean, whatever value P is, that can give you a head or a tail, right? It's just that what probability is being assigned to that. Huh? Probability of heads and tails is the same, and if you write down the graph saying that, okay, that there are this many edges, let's suppose the graph G, so n vertices, m edges. Okay, so think of this as labeled. So I don't want to go into graph isomorphism. So graph G, all the nodes have identities 1 to n that are m edges. What is the so if the coin tossing probability is P, what is the probability that I get G by coin tossing? After doing this process, what is the probability that I get G? Is my question clear? That now I'm going backwards. So this is the standard machine learning way. I have a model, right? And I say that the data is being generated by the model, but okay, I don't have all the data, I have one instance of the data. What I'm saying is that what is the probability of getting this data, this particular data point, according to your generative model? Well, no, let's just do it with P first. Let's just not do it with half, huh? It will be P to the power M, 1 minus P to the power NC2 minus M, right? Because this graph can only be obtained if in all the places where you are actually seeing an edge, you did turn out to be, the coin toss did turn out to be a head, right? And there are M small m edges, so the probability of getting these small m heads is P to the M. And also it has to be the case that wherever wherever there is no edge, it must have been the case that I got a tail. So there are n choose 2 minus small m such pairs, and I must have gotten a tail in all of them. And the probability of that is 1 minus P to the power n choose 2 minus m. Now the only place here where anything about the graph G comes in is this. So now it's easy to say that if I plug in P equal to half, because this and this become the same, it just becomes half to the power n choose 2. Basically saying that I'm assigned, see, I mean, the same probability, and see, I mean, this fits in. Because what is the possible graph, what is the possible number of labeled graphs on small n vertices? It is 2 to the power n choose 2. Right? And I'm assigning the same probability to all of them. Right? If I do this coin toss P equal to half. Right? So this is, see, these are just intuition checks, just to understand whether we know how to work with this model. Okay, so let's move on. Okay. Okay. So now I'm asking more interesting questions about this graph. Right? Specifically, here is what I'm asking. Right? So think of this P as a knob now. Right? What we'll do, this P goes from 0 to 1. Right? Clearly. I understand what happens here because you get the empty graph. I understand what happens here because you get the clique. Now suppose I start increasing P from here onwards. What happens? Right? Of course, somewhere, I mean, your intuition sort of, you have some intuition. Somehow the graph will become, the resulting graph will become denser and denser. And because after all, we have to somehow interpolate nicely from an empty graph to a clique. So somehow it should happen, right? But let's understand some of these graph properties. Suppose we are asking that, okay, that suppose I am at some position, some p value here, some value p here. I mean, I should not call it a p value. That's a different connotation. So, is the graph connected? Right? I mean, again, this question does not make any meaning per se as I asked it, because as I said, that all possible graphs can be obtained. So therefore, the only reasonable way of framing the question is to say that what is, if for a particular value of p, what is the probability that the resulting graph is connected? That's the only question that makes sense. Because, I mean, you do an experiment, you might get a disconnected graph, you do another experiment, you might get a connected graph. The point is, if you do infinite number of these experiments, what is the fraction of times that you get a graph that is connected? Okay? And let's think about the two extreme cases. P less than or equal to 1 by n versus P. Let's think about this extreme case. Suppose P is greater than or equal to half. What do you think? Is the graph going to be connected? P equal to half even, let's say. Is the graph going to be connected with high probability? Yes. Very good point. Very good point. Very good point. So in fact, what we'll see is that how to get to this seemingly hard mathematical question using this simple way of generating the graphs. But thank you for that. That's a very good point, because as Professor was saying, that really, as we were saying, that P equal to half, we are giving a uniform probability to all the graphs. So then, effectively, this question is asking that what is the fraction of graphs that are connected of all n choose? That seems like a tough question, tough nut to crack. However, we'll see that, if you think about it this way, and this is really the beauty of the theory. If you think about it this way, the answer, it becomes easy to analyze this question, because we'll be able to analyze it in this class. And in fact, we'll be interested in smaller regime of P less than equal to 1 by n. Okay, let's say P less than equal to 1 by n, and then we start pushing P a little up. Okay, so how to analyze? That is the question, right? And again, I mean, I won't, as I told you, I won't go into the very deep sort of. Give you pointers. I'll provide you a very basic outline of the proof. I mean, I like to take very, very simple cases, right, and then try to work through it. So take any node, let's say 1. So let's say P equal to 1 by n. P equal to 1 by n. We are at this step. So take any node, right? So what is the, and let me try to ask this very simple alternative question. What is the probability that it has degree 0? It is 1 minus. So it has degree 0 if all the coin tosses turned out to be tails, right? So there are n minus 1 coin tosses associated with it, because node 1 tried to form an edge with. This is the wrong picture. I think this is the. So I'm sorry about that. So it did n minus 1 coin tosses. All of them turned out to be tails, and the probability of one tail was 1 minus 1 by n. This to the power n minus 1. So this you can roughly say is e to the minus 1. So I mean, yeah, I should have written n minus 1 there. But anyway, this roughly is like e to the minus 1. You can even sort of, so without going into that, you can even get it directly from this Poisson thing that you are saying. So then thinking about it, sort of taking a step back, we took any arbitrary vertex, and then we say that the probability that it has degree 0 is e to the minus 1. So therefore, expected number of nodes that have degree 0 is really this much, n e to the minus 1. Again, by linearity of expectation, because every node has this probability of having degree 0. So therefore, the expected number of nodes of degree 0 is number of, I mean, so think of trying to make a node to be degree 0 to be a trial. The number of trials is n, and then the probability of trying to make it, the fact that it becomes degree 0 is e to the minus 1, and because by linearity of expectations, this is this. Okay. So then, and it's not very hard to show that the number of expected number of, that the real number of nodes of degree 0 nodes is going to be concentrated around that. There are, you can, I mean, if you want, you can sort of, I mean, you can appeal to central limit theorem. However, if you want to get sort of quantitative bounds, there are better tail inequalities, which tell you, which will, Chebyshev-Chernoff tail bounds, which will tell you that the number of degree 0 nodes is really concentrated around that. So therefore, I immediately get as an answer, right, that for p equal to 1 by n, the graph is not connected, right, because there's a bunch of degree 0 nodes, really, right? So the graph is not connected. So then, so what? What is interesting about it? And in fact, with a little bit of more work, it is not very hard to show this, right? And well, I should say little, but I mean only if you have done a branching process class. With a little bit of more work, it's possible to show this, that for p equal to c by n, where c is anything less than 1, right, there will be a bunch of components of the graph, right? I mean, we already saw that there will be a bunch of components because there will be a bunch of degree 0 nodes, and all the components will be of, the important point is that all the components will be of size at most log n. Right? So okay. So in any case, I mean, in fact, if no, I mean, so I don't know. This is the big O order notation, and this is the only thing from the order notation that I'll use. What it means is that there is some constant C, right, that I'm not writing explicitly, such that all the components are of some universal constant, such that all the components are of size, not the C, some constant capital C, such that all components are of size less than the capital C times log n. And this holds as long as the coin tossing probability is small c by n, where the small c is less than 1. Then magic happens, right? Supposing I have p to be some small c by n, where c is slightly more than 1. And by slightly, I even mean like n to the power, I mean, you could certainly make c to be much larger, but c to be something like 1 plus n to the power minus 1/3 is also fine. Basically, just teeny bit less than 1. And suddenly, things gel together, right? Suddenly what you see, that there exists a giant component, what we call, this is known as a giant component, because it is, the size of this component is going to be some beta times n. I'll tell you what beta is. Some beta times n plus, plus small order terms, because, we don't really characterize it that, that sort of precisely. Plus minus some small order, some small o of n. So small o of n means, so I call fn to be small o of n if limit, I'm sure a lot of you know this, fn by n tends to 0. This is the definition, sorry. This is the definition of small o of n. For all limit n tends to infinity, so that's fine. Okay, and beta is a constant that depends on c. In fact, we'll derive it, how beta depends on c. I'm sort of saying very confidently that we'll derive it. Okay, we will derive it. So how beta depends on c. So why does this happen? Why is, so basically there'll be one giant component that sucks up most of the energy in the room. Then there'll be all the other components will actually be of size less than order log n. Okay. So this at least can try to explain that. That if this happens, this at least we can try to explain that. Look, even if nothing very specific is happening with respect to the designing of the network, even if everybody was acting randomly, I do expect to get a sort of a giant component for reasonably. C to be. This p to be 1 by n is not a very large value of c, right? 1 by n is not a very large value of p, right? So yeah, as long as p, the connection probability is a little bit high, I do expect to see a giant component almost surely. Okay? So how do I show this? So again, here comes a little bit of this proof kernel thing. Here is how we show this, right? So imagine this as follows. So imagine that you're taking a particular node, right? And if you have done some graph algorithms class, imagine trying to do a BFS breadth first search from that, or just trying to grow a tree from that, right? When you generate, when you sort of have neighbors, you are trying to sort of generate some tree. You're trying to spawn offsprings or whatever you call it, right? So the number of neighbors of a node follows this Poisson distribution, as you have told me already. It follows a Poisson distribution with expectation c, because n times c by n is c. Okay? So imagine this branching process in which we are starting from a node, we generate a number of children, right, which are its neighbors, and the number of children that we generate follows this distribution, this Poisson C distribution. And then I keep on going, right? So now the process stops when no more children are spawned, because it's possible that at any particular, everybody gets one chance at spawning children. At any particular generation, if nobody spawns any children, that ancestry is dead, right? And the process has stopped, right? So the question we're going to try to answer, right, is that what is the probability? And here's what we say, that the probability that the start node belongs to the giant component is basically the probability that the process does not stop till infinity. This is where I'm sort of fudging things a little, because there's a finite limit and so on, but this is basically the idea. Right? That if I say that this process runs off, continues till infinity, I get to say that this starting node belongs to the giant component. And I'll characterize this particular probability. Right? It's easy to characterize this particular probability, it turns out. The way to characterize this particular probability is to look at it this way. Say that suppose this particular probability is Q. Right? The probability that the process goes extinct. Right? So 1 minus the probability that it goes to infinity is Q. So the Q is the probability the process goes extinct. So Q follows this recursion, right? So and this is a very, very simple recursion. So I say that, okay, suppose the first node has generated I children, right? So the process goes extinct if the first node has generated some I children for some I, sum over all possible I, and then all of these all of these ancestry of these I children went extinct. Well, only then I can go extinct. Okay? So now I can write down the probability of this. I can write down the probability of this. Well, the probability of this is basically Q to the I, because that's the definition of Q. And all of these are independent things, right? And the probability of this, probability that the first node generated I children, is really again a Poisson with parameter C by n. Sorry, I should have written C. Poisson with parameter C, and then the random variable takes the value I. So I've made a mistake here. I'll just quickly correct it. I try to make it work, it doesn't always work anyway. This is what it should be. Okay. So then I know that K follows this recursion. And if you just unplug this recursion, you exactly get this equation that we were writing down. Basically, it's just algebra beyond this. This is really the only observation. After that, it's just algebra. The probability that the process goes extinct, which is the same as the probability that the node does not belong to the giant component. You can get it by solving this equation. And so 1 minus q, if you rewrite this equation in terms of 1 minus q, that will give you the probability that the node belongs to the giant component, and therefore, that is the fraction of nodes that belong to the giant component, which you can sort of see, as follows. So this is how we analyze it. Let us go to some other things, right? What does the degree distribution look like? This you already kind of know. What does the degree distribution of this graph look like? Yeah, basically, right? So I'm more asking that. So in effect, in terms of so all the nodes, all the degrees are a binomial random variable, right? So if I plot the distribution of these degrees, how will it look like? Again, maybe this again is a trick question. It's really a way of seeing sort of trying to reach to your other ear by turning around your head. But it will be a binomial thing. It will be a binomial thing. Effectively, you're plotting it for large n, it will look like a Gaussian. It will look like a Gaussian with mean n times p and with variance square root np 1 minus p. Okay? So, in effect, in terms of the graph properties, this graph is effectively regular. Right? It's effective because the degrees are like square root np plus minus square root np. Square root np is like small o of np. Right? So the graph is effectively regular, huh? But not really. Not really. So okay, and maybe I'll throw this as a question for people to think about. What do you think the highest degree will be? With high probability. Again this is with high probability. So with high probability, will the highest degree be let's say p equal to half. That is a simpler setting. Let's say p equal to half. So the average degree, well let's say p equal to 1 by n. Maybe that is the more interesting part. So p equal to 1 by n, or some c by n, for some, so think of c as like 2 or something. So therefore, even 1. So therefore, the expected number of edges of, expected degree of every node is t. What do you think the highest degree will be? Huh? 4? Yeah, why? That is true. Well, your argument is solid, but it also shows the fallacy of this argument, which also shows the fallacy of any hypothesis testing kind of settings, right? You say that oh, this is going to be a Gaussian. I'll show you because I'll flesh out your argument. I'll try to flesh out your argument, and then we are saying that okay, it follows a Gaussian, more or less a Gaussian, and we are saying that the variance of this Gaussian is like square root the variance of this particular quantity, which is square root np times 1 minus p, right? So therefore, we know that in a Gaussian, 99% of the times you are within 3 sigma. So 3 sigma is like 3 times this, right? So plug in p equal to 1 by n. So basically, np times np is like 1 plus let's say 3 out here, 3 times 1, so that's like 4. That's what you're saying, right? If I'm not mistaken, right? So 99% of the times I stay within plus minus 3 sigma of the mean. However, right, here the number of trials that we are doing, because the number of nodes that we're looking at is also growing with this n. So therefore, if you stick the probability to be 19%, that means that 1% of the nodes, which is 0.01 times n, will have degrees that are actually higher than this 4, which is what happens when you do hypothesis testing multiple times. That you try to interpret p-value as, in the sanctimonious way it is interpreted, which is not actually correct. But anyway, but That is a problem, right? So I really need to, if I want to say that, the maximum degree is less than something, I really need to go far out into the tail, such that the probability of this part, what is remaining, is small o of 1 by n. Because I'm looking at the highest degree. I'm doing a bunch of trials. I'm tossing coins for all the, generating a Poisson random variable for all the nodes and then looking at the maximum. And in fact, it turns out that you can say that the highest degree is basically theta log n, growing with n, even if e is a constant. This is important. I'll tell you why this is important, because a lot of these come in sort of, when you, I'm sure all of you have designed all these, have used all these dictionaries in Python and other hash tables. This is exactly the analysis that comes in here. That even if you have a hash table that is perfectly random, there'll be some hash bucket that is overloaded. Right? And that is, this highest degree is that hash bucket. Anyway, not sort of talking into going too much. Okay, so here's another simple question. What is the length of a shortest path between any two pair of nodes? What do you think? Why is that log n? Okay. But, argument, intuitively? Again, we are not talking completely formal, but intuitively? So I like to think of it as follows. That suppose you say that I have two friends, and each of these two friends have two friends each. Each of them have two friends each. Each of them have two friends each. How long can the process continue if the number of people in the world is n? How long can the process continue? Log n steps, right? Until you sort of turn back and reuse some of the friends. In the setting that we have, again, have to bound the probability that you're going to reuse some of the friends, but it's not much. You can say that you can basically use this, this intuitive argument to say that within log n steps, you will reach everybody, because there's only that much you can do. Okay, so here, so now here is this last step. Right? We already saw that at c bigger than 1 plus epsilon, right? The graph is still disconnected with high probability, but it forms a giant component, right? So I guess I didn't show you, or maybe I did. Yeah. In fact, the same proof of degree 0 shows that at c 1 plus epsilon, think of epsilon as a small constant. The graph is still disconnected with high probability because it has degree 0 nodes, but it will have a giant component at c equal to log n, right? Which means that when the probability is like log n by n, I can guarantee that the graph will become connected with very high probability. How do you think this argument will look like? This is actually an easier argument, in fact. I'll draw the picture and then it will come to you. So imagine the graph is disconnected. So imagine, or rather imagine this. Take any subset of the vertices. So take any subset of the vertices of k nodes. Take the other n minus k, right? So how many edges are expected to go between these two vertices? Number of edges expected is the number of pairs between these two sets. Maybe I sort of just misspoke. How many edges are expected to go between these two sets? Right? The number of pairs between these two sets, where one element of the pair belongs here, one element of the pair belongs here, is this, right? The probability of that pair turns out to be at head is p. So therefore, basically I'll sort of approximate this by kn times p. This is really the expected number of edges I sort of will see between these two subsets, right? So at p equal to log n by n, this quantity becomes k log n, basically, right? Because this n and this n cancel out, and this is so it's again this is whatever you call it. This is a Poisson thing. This is a Poisson thing with expectation k log n. Or you can apply this tail inequalities to say that basically once a Poisson random variable has expectation k log n, it is very, very concentrated around that expectation, right? So, so you can say that I can apply either Poisson distribution itself or go into tail inequalities to say that if x follows k log n, probability that x will be less than, well, if these two vertices, if these two subsets have to be disconnected, the number of edges has to be 0, right? Probability that x is less than, let's say, some alpha times some x minus, some expectation of x minus t will be less than equal to exp of some minus t square by k log n. So like Gaussian, this is kind of like the Gaussian thing, but you don't need to apply CLT. You can get it by chain of bounds, and you can say that. So in our case, if these two vertex sets have to be disconnected from one another, this x has to assume 0. Therefore, you need to plug in t to be equal to expectation x, right? And if you plug in t to be expectation x, what you see, t to be like k log n, you get to see that this probability is very, 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 very tiny. Except that there are many different possible partitions, exponential number of partitions. But you can say that, you can again do a little bit of argument to say that you can say that any of these partitions, partition a vertex set any way you want. None of these partitions, I will disconnect. I will not. Number of edges between these two parts of the partition will be very far off from its expectation. Basically, that's the idea. Right? So basically, what it says is that as long as p is like log n by n, everything really happens according to the expectation, right? And because we are arguing for p log n by n, if we increase p, of course, any statement that I say to be for this domain of p, this connectivity statement also holds for a higher value of p. So therefore, even for p equal to half, we'll be able to say that the graph is connected with very, very high probability, and that gives you a pretty interesting mathematical statement about all possible graphs. Anyway, let us not go in there because our interest is more in real-world networks. Okay, so then my basic sticking point. Okay, so there's a break, right? There's a tea break or something. Okay, so then we'll continue after the tea break.